we decided to skip chapter 7F because, well, it's good to learn, it's good to learn the inverse to make you feel confident about like using the matrix in another way. But in the current study design, they cut a lot of stuff for matrices. They no longer require you to use matrices to set up like linear equations, no longer require you to do the inverse to solve for it. So because we lose a lot of lessons, that's why we decide to cut this exercise, no longer do it. So there's no impact for you to do the questions, like to do the VC exam. But I'm not sure if you remember, when we deal with that question, the unique solution, many solution, no solution problem, like the simultaneous linear equation, and want to figure out what k values can give me like those three situations. Well, that actually can be done easily by inverse rather than doing the gradient and track the intercept. It will be an easier way to use the inverse of matrices. But, well, because we won't go through this year, so we'll skip that. Let me see if we have some spare time later in the year, and if we have that, I'll go through this part with you. So it will be easily done by the concept of inverse. But we decide to skip that for this chapter now. Like your topic test won't include 7F, and also the scheme of work not include 7F as well. Okay, so we directly skip to G. Okay, we directly skip to G. G is why we learn matrices. Okay, we learn matrices, how to add, what is a matrix, and how to add them, how to multiply them, how to times the scalar factor to them. So that's the calculation, okay, operations we can do to matrices. Now, like, we will do something like dilation, reflection, transformation by using matrices. So, okay, matrices is equivalent to what? I'm not sure if you still remember last week's thing. We have 3 steps, right? We have 3 steps to do the transformation. Well, we have the original function x and y. We have the finish like after resultant function as x dash and y dash. And in the middle, I said that's a transformation description. Or let's say that's the wording. Okay, matrices is equivalent to that. Okay, matrix is equivalent to give you the wording, and it's actually easier than give you the wording. Okay, so like according to the word, I will say, for example, there's a reflection in the x-axis. What I will write is y dash equals to negative y. Okay, and there's a dilation from the x-axis by a factor of 2. Y dash equals to 2y. That's what we will get from the transformation description. We will have like y dash equals to some y, x dash equals to some x. That's what we can get from step 2. Or if we want to know what the description is, we will make x dash y dash to be the subject and then describe it. Okay, so step 1, 2, and 3, those 3 things are equivalent now. Okay, give you any of this, you should be able to write the other 2. Okay, they all belong to step number 2, but they can like swap between each other. If give you the word description, you should be able to write out the x dash y dash thing, and you should be able to write out the matrices. Okay, and give you the matrix, you can write out x dash and y dash, and you can use x dash y dash to use word description as well. Well, maybe I should change the order a little bit. This part can be x dash equals to some x and y dash equals to some y, and then I can use a matrix representation to that. So that actually should be the order. Well, transformation description can directly give you x dash equals to some x, y dash equals to some y, and that can directly give you the matrix. And matrix can directly go back to the x dash y dash thing, and therefore you can write the descriptions from that. Okay, so that's maybe a better order, but doesn't matter, they can become each other. That's all you need to remember. That's all under step number 2. Okay, that's what you get from step number 2. And step 1 is still the same, step 2 is still the same. So even though we add one new method called matrices, but remember matrices belongs to step number 2. Okay, let's have a look. What is matrices? Okay, it will be a little bit hard without skip that exercise, but let's just do one easy example, okay? Let you see why matrices can equivalent to words. So let's say there's a dilation, or there's a dilation by a factor of 2 from the x-axis. Okay, from the x-axis. Okay, what you can write according to this is x won't change. X dash still equals to x, but y dash equals to 2y. Okay, that's what you can write. Okay, that's what you can write. Now I will change this into a matrix representation. Okay, how I will do this? Okay, have a look at this. Well, I'll go through why it's like this. If I can expand, or I say less, if I can calculate the left-hand side, okay, remember row, column. Remember, like 2 times 2 matrix can multiply with 2 times 1 matrix. We have go through that calculation yesterday. So they can be times together. So row for the first one and column for the second one. Answer will be a 2 times 1 matrix. Okay, answer will be a 2 times 1 matrix. So let's calculate the left-hand side. What left-hand side can give me? So first row times first column, like row 1, row 2, and that's a column 1. So row 1 times column 1. 1 times x give me an x. 0 times y, nothing. Okay, and 0 times x give me 0. 2 times y gives me 2y. So after the calculation, left hand side equals to that. Okay, left hand side equals to this. Just a multiplication calculation that will give me x and 2y, and still make it equals to the right hand side. So remember, when 2 matrices can be exactly the same, when they have identical, okay, they look identical, they have the same size, same dimension, and all the corresponding entries must be the same. So now I say this matrix equals to that matrix. What you can tell me is x dash equals to x, and y dash needs to be the same as 2y. Okay, can you see what I'm doing here? So, well, yes, from this word description, I can get this equation. But from this matrix equation, I can still get the same thing. So that's why I said the matrix can easily replace the word. And after I do all this calculation, that can give me exactly the same thing compared to what the words, like the description, can give me. So that's why I'm explaining why a matrix like will work. Okay, so in this matrix, what we'll have, like I'll use another color. This 2 times 2 matrix is a transformation matrix. I normally use a T to represent that. Okay, that's a transformation matrix, and that's the original coordinates. And this is after, like, the resultant coordinates. Okay, so the resultant coordinates will equals to the transformation matrix times the original coordinates. Okay, so transformation matrix times the original coordinates, that will give me the new coordinates. Okay, you can't swap the order for the original matrix and the transformation matrix, because if you swap the order, they can't times together. Okay, 2 times 1 matrix can't times by 2 times 2 matrix, so they can't times together. So this must follow this particular order. Transformation matrix in the front, and then we have an original matrix there. Any questions? Okay, if we don't have any questions, let's have a look how many types of transformation matrix we'll have. So the first group is a dilation. Okay, it's a dilation. Have a look. I have 1. Okay, I have 1 at the left corner, which means there's nothing changed for the x. And there's a 2 here. This responsible for the y. Okay, responsible for the y. So 2 is the dilation factor. See, compare the wording. 2 is the dilation factor from the x-axis because it's changed y. So let's have a look. If you have dilation from the y, you change x. Okay, this diagonal will always be 0. Well, not always. Okay, in the dilation case, you will have 0 and 0. You have 0 and 0. Then this place is for x and this place is for y. Okay, why is like that? Because when you times it, this one will go times, like this number will go times with y. This number will go times with x. So that's why the first one in charge of x and the second one in charge of y. So your dilation, well, depends on what's the dilation factor, you will just change this n here. If it's dilate from the x, then y won't change. So no, dilation from x, x won't change. So x stay as 1. So y stay as a factor a. Okay, y has a factor a, like it will be ay. Well, if you dilate from both x-axis and y-axis, okay, n from the y-axis is changing x. Therefore, we have the value of x here. And then changing y, we have the value a here. So we can combine them as well. Okay, we can combine them as well. I can combine dilation together, not necessary to go one and then another one and then another one. I can combine it in one matrices. So therefore, if I give you any matrix, like transformation matrix, for example, I give you 1, 0, 0, half. Okay, if I give you this, you can say, not 1, let's make a 3 here. You can tell me this is a dilation by a factor of 3 from the y-axis and then a dilation of a half from the x-axis. Okay, that's what you can directly see from the matrix without giving you any wording. Okay, so this number, this matrix can represent the dilation already. Okay, that's the first one. Why we have 0 and 0 here? Because this 0 will be times with y. You don't want any y when you do with x. So that's why you want y disappear. So we have a 0. So this 0 will times with x when you circle the row. So I don't want any x in the y expression. So I'll make the x become 0 in the second row. So that's why we have 0 and 0 on the diagonal. And then those two numbers there. Okay, reflection next. Well, the first three reflections is very easy to think. Well, it depends on when x is negative and when y is negative. If you reflect in the y-axis, your x will be negative. If you reflect in the x-axis, your y will be negative, while the others will stay as 1. If you reflect in both x and y, you will have -1 and -1. So the other two places still 0, as I explained before. You don't want any expression in the you don't want any expression in y with x, so you want to make the x disappear in the second row, and in the first row you want y disappear. So that's why I have 0 and 0 on the diagonal. And there's a special one. Okay, there's a special one. We haven't done this in the we haven't done this when we talk about the dilation, reflection, and transformation like last week. So this a new transformation we can have is a reflection in the y equals x. Okay, if you reflect the graph in the line y equals x, what you will have? What is it? Inverse. Okay, reflect that, you will get the inverse function. The x become y and the y become x. So you see your new x become the old y and your new y become the old x. So that's the reflection in the line y equals to x. So okay, well, ignore this one. Okay, I don't want to go through this one. It will make more complex. You just need to remember reflecting the line y equals to x. That's what we require, is the inverse function. Okay, remember that's the inverse. We haven't talked about that in when we talk about like last week when we talk about transformation. This is very unique in the matrices. Okay, in the matrices. So let's have a look. Reflect in the line y equals x without doing the matrix yet. We just think about your x dash will become the old y, and your y dash will become the old x, right? That's what you want to achieve. That's the reflection, what the reflection will give you. Because you know it's the inverse, you swap the x and y values. Now let's do the matrices. Well, the transformation matrix looks very unique. Okay, originally this line will be 1, 1, this line will be 0, 0, but we swap it. Okay, we swap it. Let's times this xy, and that should give you the new point. Okay, that's transformation matrix times the original coordinates should give you the new coordinates. So that's the formula. Let's check whether it's true or not. Well, definitely needs to be true. You just check it. Okay, we use the row to times with the column. Okay, row times with the column. 0 times x, x disappeared in the first row, but 1 times y give you y. 1 times x in the second row, that give you x. 0 times y give you y, disappeared. See if you equalize that, x dash will be the same as y, y dash will be the same as x. So we will achieve what we want in the end by using this matrix. So this matrix is just replace 0 by 1, replace 1 by 0, and you will have this transformation here. Okay, so you need to remember what's the inverse matrix, transformation matrix looks like. So everything here is called transformation matrix. Okay, so that all of this needs to times with the original coordinates and give you the new coordinates. Okay, times with the original gives you the new coordinates. Okay, we have talked about reflection. We have talked about dilation. The last thing we will talk about is a translation. Okay, it's a translation. Well, translation is so easy. Okay, translation is so easy. You know, like you will times, for example, okay, the new point will equals to what? The new point will equals to, well, let's say 3, 0, 0, negative 2. Okay, let's have a look. Why I give you this? You can tell me this must be a dilation from the dilation by factor of 3 from the y-axis, dilation by factor of 2 from the x-axis, and reflect in the x-axis as well. Because we won't separate the negative, like you know, in I said dilation factor can only be positive. When there's a negative, it must mean reflection. I can combine dilation and reflection together in one matrices. Okay, everything can be done in one matrices. Okay, one last thing is translation. Okay, if you do matrices, you must follow the DRT order. Okay, you must follow the DRT order. Well, unless you have bracket, you want the transformation happen first, you need the bracket. But I think it will be easier for you to do it by DRT order. When the question, if they give you a transformation matrices, it might not be in the DRT order, but I'll show you that. But when you do it, when you're trying to write a matrices, you need to follow a DRT order. Okay, why we follow DRT order? Can you see all of this happens will be dilation, reflection happens after that, and we add a 2 times 1 matrix. For example, I add -1 and 2. This means there's a left-hand side movement, 1 unit. Well, I'll move 1 unit to the left and 2 units up. Okay, the top one in charge of the X movement and the bottom one in charge of the Y movement. But because we don't have, we always have the plus sign here. So therefore, we will put the left shift and down shift by minus. So the -1 means the left and the +2 means up. Okay, the top one is changing X values and the bottom one change Y values. So translation matrix is easily a 2 times 1 matrix, and that just tell you the units you move and the direction you move. Okay, that's all about matrices. Okay, that's all about matrices. When you expand, when you calculate the matrix, you will have x dash equals to some x and y dash equals to some y. Therefore, you can also talk about what kind of like in words, okay, to describe it. Okay, example 1. Let's do one example here. Okay, let's see example 1. Find the image of the point 2, 3. Okay, this is very interesting. You can sketch the diagram and you can tell me the answer, but I want you to understand how matrices works. Okay, just always remember the new point equals to a transformation matrix. Well, I don't know what it looks like, but it will be a transformation matrix times the original point and add the movement. Okay, that's always the formula. That's always the formula. And sometimes the x dash y dash can be represented by another way. It will be t bracket xy. Very easy to understand why we express it in this way. It's the new point, the old point under the transformation. Okay, what's new point and the transformation? Old point and the transformation give you the new point. So they are equivalent. Okay, so it's the original xy put into the transformation. What do you have? You know you have x dash y dash. So when you see t bracket xy, that's equivalent to x dash and y dash. Okay, that's equivalent to x dash y dash. So that's the only formula we have for transformation matrices. Yeah, that's the only formula we use for transformation matrices. Okay, let's have a look at the first one. The first one is find the image of the point 2, 3. Well, A says and the reflection in the x-axis. Okay, can you tell me what's the transformation matrix for reflection in the x-axis? Okay, let's say that's the place 1, place 2, place 3, and place 4. Let's write in order what number we should have. First one, 1, second, 0, third, 0, and -1. Okay, -1. So that's the transformation matrix for a reflection in the x-axis. Okay, remember I will times the transformation matrix by the old point, okay, original point. So the original point in this question will be 2, 3. So I will times 2, 3 onto this transformation matrix. After the calculation, I will have the new point. Okay, after the transformation, after the calculation, I should have x dash and y dash. So how do we calculate that? The row and the column. That will give me 1 times 2 give me a 2, 0 times 3 will become a 0. Second one, 0 times 2 is a 0, -1 times 3 will be a -3. So the after transformation points will be 2, -3. Okay, top is x value, bottom is y value. So it will be a 2, -3. Okay, for the second one said this is a dilation factor k from the y-axis. Okay, let's think about the transformation matrix first. Well, same position 1, 2, 3, 4. What I should have for 1? Okay, 2, 0, 3, 0, last one, 1. Okay, so that's the transformation matrix for a dilation from the y-axis, and I will times that by the original point. So we have K0, 0, 1 and times with 2, 3. Okay, times with 2, 3. Let's calculate that. 2K for this one and 3 for the bottom. So the coordinates will be 2K, comma 3. There will be a 2K, comma 3 for this one. Okay, that's how we use matrices, okay? But it will be harder questions. This is just like tell you how to use it, but we will combine different transformations together later. Okay, that's for a single transformation. Before we do example 2, let's do example 3. I think it's more appropriate to do 1 and then 3. Okay, for 3, it says find the image of the point 2, -3. Okay, remember the new point, okay, equals to a transformation matrix times with the old point and then plus the translation. Okay, that's the order. Now what we see is find the image of that point. That point is 2, -3. Okay, that point is 2, -3. That's the xy. Okay, that's the xy. And then what we have a reflection in the x-axis. Okay, let's do this one first. Reflection in the x-axis. Okay, what we should write? What's the first place? 1 and 0 and 0, -1. Okay. After that, we have then a dilation of factor k. Well, that's number 1. A dilation of factor k from the y-axis. Okay, this is the important thing. Although I can combine it in one matrix, okay, I can combine it in one matrix, but I don't want to do that now because you will meet some other type of transformation when you can't combine. What you will do at that time, if something happened first and then another thing happened, okay, which one happened first needs to be the closest to the original point. In other words, the second transformation, well, I have a first transformation matrix, right? And times another transformation matrix. That one needs to be in the front. Okay, so that's your first and that's your second. You can't swap that. A lot of students say, oh, first here, second here, third here, and then we times with xy. That's the wrong order. Okay, you have, when you meet questions can't combine together, you will get the answer wrong. Just let you know, if you change 1 and 2 in this question, it's not going to be wrong. It's still the same thing because the order is not important for dilation and reflection. Which one you do first, which one you do second, that will give you the same answer. But when you combine the translation in it, it will be different. Also, if you combine the reflecting line y equals x, that will be different. Okay, that will be different.
So this transient reverse and then dilated, you put the dilation.
Okay, if you say a translation first, yeah? If you have a translation 1, 3, for example, that's a translation 1 to the right, 3 up, and then we bracket that, and then we put translation, and then if you have another one, we put another one in the front. Okay, so you must follow this order. If the order is wrong, the answer will be wrong. Well, in some case, when the order doesn't matter, you will have the same answer. For example, this one, you can put 1 first and then second, or 1 second first and then 1. But you need to remember the correct way of doing transformation. The way you need to write it is which one happened first, which one needs to be the closest to the original points, and you write everything into the front. And any further transformation will be right into the front. So that's T1, that's T2. Okay. So a dilation from K from Y, so that's what I will have. You know that's what that's equivalent to. That will equivalent to a K0, 0, -1. Okay, so two things can represent by the same matrix. But why I put 2, I want you to understand like how to write the order. Again, which means I can do this. They are equivalent. Okay, they are equivalent. But why they are equivalent? I will show you that. You can multiply matrix together. You can multiply many transformation matrix together to get a final result. Okay, get a one matrix to represent all the dilation, reflection, reflecting y equals to x, all of it. In this T matrix, you can't see any translation. Okay, translation must be at the back. You can't see translation. All of this is dilation and reflection and a combination between them. So if I want to times T2 by T1, what I will have? I will have a 2 times 2 matrix. Okay, row 1, row 2, column 1, column 2. Row 1 times column 1, I get K. Row 1 times column 2, I get 0. Row 2 times column 1, I get 0. And row 2 times column 2, I get -1. Can you see they are the same? Can you see this one and this one's the same? So the second one is just a combination between T1 and T2. Basically times them, multiply them. Okay, so it will give you the same thing. It will give you the same thing. And I can further calculate that. Okay, row and column. What I have here is a 2K and a 3. So the new coordinates is 2K, 3. This question is not hard. Okay, I can even do this by one step. But the thing is how to write different matrix in the correct order. Okay, T1 must be the closest to the original points, and we write any further transformation into the front. Okay, and example 4 first. Okay, example 4 first before we do example 2. Okay, all the questions we do before, okay, 1 and 3, they only talk about a single point. Okay, that's a point after the translation or transformation what we have. But now example 4 is a more general case. Okay, I'm not talking about points. I'm talking about all the points. Okay, all of this like on the curve. And then we can apply the transformation into equations now. Okay, again, before that, we still use the same equation. The new point equals to t times the original and plus any translation. Now let's have a look at the questions here. Express the composition of transformation dilation of factor k. Okay, dilation of factor k from the y-axis, that's the first thing. Followed by a translation defined by this. Mapping a point xy, the old point, onto new point x dash y dash as a matrix equation. Hence, find xy in terms of x dash y dash. Okay, let's do step by step. I have two things happen, two transformation happen. I want to set up an equation. Okay, set up a matrix. So the matrix I should be able to set up is the new point equals to the, well, dilation happened first. So it's K001 times with the original points and add a translation AB. Okay, that's something we can write. Okay, that's something we can write. Alright, the first thing for matrix question, the first thing is set up the matrix. The second thing will be times it, calculate it, okay, and equalize them. So we'll calculate that first. So we calculate times first and then adding. Okay, so we want to calculate this. We will times it. This is very easy to do, like the multiplication, because a lot of zeros in the transformation matrix. So a lot of things just become zero. It's easier than what we do yesterday. Okay, if you calculate this, I should have kx and y. Okay. Next question is, when will two matrices can be add or subtract? Same size or same dimension. So right hand side, those two have the same size, so I can add them. So x dash y dash equals to kx plus a and y plus b. Okay, just add the thing. Okay, that become one number, that become one number. So that's a 2 times 1 matrix, that's a 2 times 1 matrix. So what conclusion we have is x dash equals to kx plus a and y dash equals to y plus b. So I have set up the matrix, I have calculated, and then I will equalize them. The last thing we need is hence find x and y in terms of x dash y dash. Okay, before we do that, let's have a think. This is the same thing we achieved from a wording description, right? When we use wording description, I will achieve x dash equals to some x and y dash equals to some y. So the matrix will give me the same thing. That's why I said the wording description will be equivalent to the matrix expression. Okay? Now, I want to make x to be the subject. So x equals to x dash minus a over k and y equals to y dash minus b. Done. Okay, last step. Remember, I can substitute that into the original function to get the resulting function. Remember that? I can replace x by x dash minus a over k, replace y by y dash minus b. I have get the resultant function if I know what the original question is. Okay, we will do that tomorrow. Okay, we're not going to go through the application bit yet. So that's the basic. Okay, that's what we can do for a transformation matrices. Okay, these 3 examples is very important and it's directly related to what we're going to do tomorrow. Okay, very important. Any questions before I start example 2? Yes? The question is just hence find x, y in terms of x dash, y dash. They want an expression. Well, why we need to make x, y to be the subject? Because I want to substitute that into the original to achieve the result later. But in this question, they stop here. Okay, that's it. In order, from the left to right. From left to right. You can do those 2 first. Okay, you can do those 2 first. Without swapping the order, you can do any 2 first. But this result, this is still in the front, and times the result of that. You can do that. But when you make, like, you can't swap them. You can't go the first one times with 2 and negative 3. You can't change the order, but you can do any 2 connect together, you can times it. And the order still remain the same. Okay. Any other questions before I start next one? Okay, these 3 examples very important. We use these skills for tomorrow. Okay, we use these skills for tomorrow. I think tomorrow is the last exercise. Okay, tomorrow is the last exercise. We have a challenging question, it's a combination question there. Okay, before we go through the last exercise, we do something which is not that important, but it's a very good practice. Okay, so what, like all the transformation we learned so far, they all call the linear transformation. Okay, all called the linear transformation. It won't change the shape. Okay, it won't change the basic shape. It's only like except the reflection in the line y equals x, that will change the graph. But like that's not really belongs to a linear transformation. But all the things we have learned before, they are all linear transformation. Not going to change the nature of the function. Not going to change the type of function. Okay. Example 2 said, consider a linear transformation. You know, let's have a think. All these transformation we have. On either diagonal, there's always a 0, 0. Can you see that? Like 0, 0 there, 0, 0, 0, 0, and 0, 0. Like we always have a 0, 0 on one diagonal. But for example 2, it just said consider a linear transformation T. Maps this point to that point. Map 2, 4 to -3 and -1. And I want to find the image of -1 and 1. Okay, I don't know what's the transformation. I have no idea what's going on to that transformation. What all I know is linear transformation is a 2 times 2 matrix. Well, most of times have diagonal have 0, 0. But I can't 100% make sure after all this combination, for example, there's 100 things happen together, and after I times combine them into 1, I don't know what will happen. I don't know whether they'll still have a 0, 0 on the diagonal or not. I don't know like any information about that. So this transformation matrix, I will just use A, B, C, D to represent. Well, even though we have 0, 0 on one diagonal, doesn't matter. After the calculation, I should have the 0, 0. Okay, I can solve out 0, 0. So I will assume there's 4 numbers in this matrix. This matrix is not a single dilation or reflection. It can be a combination of about like 10,000 things. Okay, I'm not going to give you that much, but like it's a combination of a lot of things. So what thing I can set up is the point 1, 3 undergoes this transformation. I achieve the point -2 and -3. And the same matrix can make the point 2, 4 into -3 and -11. Okay, this is more for understanding for matrices. This is how I can set up a transformation matrix. Okay, that's how I can set up a transformation matrix. So after I set up the matrix, set up according to what they give us, what we need to do is equalize. Okay, calculation and equalize. So for the first one, what I will have is A plus 3B and C plus 3D. Equals to 1, 3. Oh, sorry, 1. Copy the wrong thing. -3 and -2 and -3. For the second one, I have 2A plus 4B, 2C plus 4D. Equals to -3 and -11. Okay, calculation. That's the calculation step. Set up, calculate, equalize. Third thing is equalize. So A plus 3B must be the same as -2. C plus 3D must be the same as -3. Well, that's from the first thing. And from the second, we have 2A plus 4B equals to -3. And 2C plus 4D equals to -11. Okay, set up the equation, calculate the equation, equalize them. Very obvious what you can do now is simultaneous equations. To solve 2 simultaneous equations give you A, B, C, D value. So to solve that, have 2A plus 6B equals to -4. So 2b equals to minus 1. B equals to minus half. A equals to minus 2 minus 3. B. Plus 3 over 2. That's a minus a half as well. A little bit short of time, so I just do the calculation by myself. You can just do that. Everyone can do the linear simultaneous equation. Not sure if my calculation is accurate, but that's what I have. You can check your answers as well. Don't think I can finish, but we just left a little bit. Just do your calculation, don't rush, and check whether we have the same thing, and we can continue tomorrow. Okay, that's what, no, next week. Remember to, we almost finished here, okay? And you can do the whole exercise now. We just left a little bit.